Good morning, dear colleagues, dear students. Today we will continue solving different tasks of radiochemistry, and today we will talk about isotopic exchange. In principle, if we have two compounds, or it can be even the same chemical form, for example, we have quite a simple example, this acid, and this molecule has only stable iodine, and if we add some radioactive iodine in this system, then it will be possible to exchange this radioactive iodine between these two molecules. Or to make it more clear, we can take acid and, for example, salt, and then it can be an exchange of isotopes between these two compounds. This is very important when we are talking about the radiopharmaceuticals, for example, or when we are talking about the tritium waste during the decommissioning or radioactive waste management, because in the case of radiopharmaceuticals, the labeled compounds, the radionuclide inside the radiopharmaceutical can be exchanged with other atoms of the same element, but stable atoms that are present in the organism and thus dilute their specific activity, let's say. And for tritium waste, tritium is very mobile, very mobile tracer radionuclide, and it can easily exchange atoms inside the organic molecules or in water molecules or whatever. And today we will look on what are the dependencies, what are parameters that can control this isotopic exchange, and how to calculate the specific activity that can be achieved by different methods. So when we have this equilibrium, we can write them in a more common way. For example, like this, we have compound AX and labeled compound BX, and there is an isotopic exchange between these two compounds. So and we can write the constant, thermodynamic constant for this reaction as usual. So it will be activity of our AX labeled, activity BX divided by activity AX and activity BX labeled. Okay. In thermodynamical equilibrium, the specific activity will distribute it between all the compounds homogeneously, let's say. That means that the specific activity of all the compounds will be the same. How to express it? If we know the total amount of activity, A total, and we know the number of X atoms, so number of X as an element, so it will be a number of AX, for example, plus number of BX. Or the same. It will be a number of AX labeled number BX. And then the specific activity of this element X in the system will be A total divided by this number of X atoms. So again, what is important, that the activity will be distributed homogeneously between all atoms of element X. So, but if we are talking about the dynamic equilibrium, it means that it will take some time to reach the equilibrium, and the isotopic exchange can be not reached at a certain time. So that means that at some time before the equilibrium, the distribution of the radionuclide of the activity will be not homogeneous, let's say. And in this case, we are using the degree of isotopic exchange that can be expressed as the activity of our compound at a certain time t minus its initial activity divided by the activity at this time t minus activity at equilibrium. So if there was no activity at the initial point, at the initial time, then the A0 will be 0 and the expression will be even simpler. So this is a very simple equation, and we will use it as well. So now we will start to solve the task. So it is a very brief introduction to the understanding what is the isotopic exchange, and I will clean this desk. The first task is rather simple, but very important. We have organic solution of ethyl iodide, and we add to the system aqueous solution containing calcium iodide. In this case, the organic and aqueous solution, they are not mixing, so they are in contact, thus the iodine can move from aqueous phase to organic phase and vice versa. And the question is, what is the amount of the calcium iodide that is labeled with radioactive iodine we should add to the system to obtain a certain amount of ethyl iodide with a known specific activity. And there is two important notes. First of them, that the calcium iodide is added without a carrier. What does it mean? So I will write again. So this specific activity of iodine. If we know the total activity of the iodine in the system, we should divide it by the total number of iodine atoms in the system, where we have iodine. So it will be amount of ethyl iodide and two amounts of the calcium iodide. because here it is calcium iodine 2. That means that in one molecule of calcium iodide there are 2 atoms of iodine. But if we recalculate the amount of iodine atoms in calcium iodide, taking into account the half-life of iodine 131, we will see that the amount will be very small. It will be much smaller than the amount of ethyl iodide. That means that we can write that amount of calcium iodide is much lower than the amount of ethyl iodide. In this case, we can neglect this member in our equation, and that means that the total, that the specific activity of iodine will be determined only by the amount of ethyl iodide. And very often, when we will see that there is no carrier. What is carrier? In this case, a carrier would be a calcium iodide with the stable iodine. So just a normal calcium iodide. But we didn't add any stable calcium iodide in our system. We have only radioactive calcium iodide in our system. And in this case, we can neglect its amount, not neglect its activity, but the amount. And thus, when we have, again, a task where we have these words without a carrier, that means that all the activity will go to the main component. Okay, so what next? Now we should understand what will be the activity, the total activity of ethyl iodide. We know the amount of ethyl iodide, and we know the required specific activity of this compound. So, thus this task will be solved quite easily. The total activity that we should add to the system, because all the activity will go to the ethyl iodide, will be equal to the specific activity of ethyl iodide multiplied by the amount of ethyl iodide. So it is 5,000 becquerel per mole multiplied by 0.1 mole. So it's just 500 becquerels. As far as all the activity that we will add to our system will go to the ethyl iodide, that means that we should simply calculate the volume of our calcium iodide solution that will bring to our system 500 becquerels. So the volume will be calculated as 500 becquerels divided by the specific activity of our solution. So it is 200 becquerels per milliliter. So it will be only 2.5 milliliter. And this is the answer to our question. So again, if there is no carrier inside our system and in the aqueous solution, then the task is solved quite simply and very fast. Again, you can see that it is quite efficient way to produce the labeled organic compound. You just mix aqueous and organic solution, and due to the isotopic exchange, you will get the labeled organic compound. And you can use it further for some reactions to label other organic compounds, etc. So let's go to the next task. Now we have again a solution of organic compound. So it is diiodopropane in benzene. So it is organic solution, and it is mixed with aqueous solution of sodium iodide. And in this case, you can see that there is a certain concentration of sodium iodide. That means that there is a carrier of stable sodium iodide in our system, and it is labeled with some radioactive iodine. So these two solutions, they are mixed, and they are stirred for a certain time, for 2 hours, and it is known that specific activity of diiodopropane became equal to this value, and we should determine the degree of isotopic exchange. So I will write here this equation again. So the degree of isotope exchange will be AT minus A0 divided by AT minus A. It should be A at equilibrium minus A initial. Yeah, sorry. So this is the correct equation, and again it is also 0. So the expression will be rather simple. It is the activity of our iodopropane divided by the activity of iodopropane in equilibrium. So we should calculate first what is the activity of our iodopropane would be when the equilibrium will be reached. So how to calculate it? First of all, we have to calculate the specific activity of iodine atoms that will be in the system after reaching of equilibrium. So the specific activity, again, of iodine will be total activity of iodine divided by the number of atoms of iodine in the system. What are the number of atoms in the system, or the moles of iodine atoms, amount of iodine atoms? We know that there is sodium iodide, so it will be number of atoms of iodine in sodium iodide, plus, again, 2 amounts of our diiodopropane. So don't forget about the indexes when you will solve the tasks. So here you can see 2 atoms of iodine. That means number of iodine atoms will be twice as number of diiodopropane atoms. We know the amount of the added activity. So it is 500 becquerels per milliliter multiplied by the volume of the sodium iodide solution. So it is 50 milliliters. And then the number of atoms or the amount of the sodium iodide, it is simply the concentration of the compound multiplied by the volume. Thus, it will be 0.04 mole per liter multiplied by 0.05 liters. So we convert milliliters to liters, plus 2 multiplied again by the concentration of diisopropane, 003 mole per liters. Very often the mole per liter is noticed as just a big letter M, and multiplied by the same volume, 005 liters. Okay. So now we have all the numbers. So the specific activity of iodine at equilibrium, so we can write it is at equilibrium, will be 2,500 becquerels divided by 0.04. It will be 0.002 mole plus 0.003 mole. So it will be 5 multiplied by 10 to 5 becquerel per mole. Okay, now we know the specific activity of iodine atoms in the system when the equilibrium will be reached. What will be the specific activity of diisopropane in the system after the reaching of equilibrium? Again, it is rather simple. The specific activity of our compound will be equal to the fraction of iodine atoms that belong to this compound related to the whole number of atoms of iodine in the system. So I will express it as at equilibrium. So it will be a specific activity of iodine atoms multiplied by the amount of iodine atoms in our So the number of iodine atoms that belongs to our organic compounds divided by the total number of iodine atoms in the system. So it will be 5 10 to 5 multiplied by the 0.003 0.005. So it will be simply 3 10 to 5 becquerel per mole. So, and now we know the activity, the specific activity of our compound after 2 hours. And so at certain time, this activity, specific activity, will be 100 becquerel, 150 becquerel per milliliter, multiplied by 50 milliliters, and multiplied by the concentration. So it is 0.003 mole. Oh, we have to divide it by the amount of. So we know the total activity. So it will be 750 becquerels in the whole volume of our compound, and then we have to divide it by the total amount of our mole per liter, multiplied 0.05 liter, by the total amount of our atoms. So it will be 7,500 becquerels divided again by, in this case, 0.0015 mole, and I got a number much higher than should be. Okay, here, yes, sorry. And here it should be 6. Still there is lower specific activity. So it should be also 6 here. 6. Let's calculate it again. So 50 milliliters of 0.003 moles. It will be 0.0015 multiplied by 2 will give us 0.03. Okay. Then, so we already calculated the specific activity of iodine atoms, and thus the only thing that we should do to calculate the activity of our propane at equilibrium is the multiplication of this specific activity of iodine atoms by the number of iodine atoms in our compound. Yes. So now this activity will be 510 to 6 becquerels per mole, multiplied by the 0.003 mole. So we already calculate this value. So it will be 1.5 10 to 4 becquerel. If I would like to calculate this value of the activity of my compound at the equilibrium with this using of the fraction, I can do it as this. So it is again activity. It will be total activity, and then it will be a fraction of my iodine atoms. So if I would like to calculate, so all the equations will be the same, and I would get the same number. And let's write it in maybe a more easier way. So it will be 15,000 becquerels. And now we know the activity, both activities. AT activity we already calculated. I just removed this. It is simply the activity of the solution multiplied by the volume of this solution by 50 milliliters. So it is 7,500 becquerels. And thus we know activity at a certain moment, we know the activity at equilibrium, and thus the degree of isotope exchange will be simply 7,500 becquerels divided by 15,000 becquerels, so it will be 0.5. So that means that only 50% of the molecules, of the molecules are exchanged, and it will take some more time to reach the equilibrium. Okay, finally we solved this task. Let's go to the next. So the next task. We have again aqueous solution and organic solution, and there is, after a certain time, after 9 hours, the activity of aqueous phase decreased from 3,000 to 500 becquerels, and we should find the degree of isotope exchange, but we have to take into account that the half-life of radioactive bromine is 36 hours. That means that 9 hours of our experiment is comparable to the half-life of the bromine, of the radioactive bromine. So how to do the calculation in this case? Very simple from one point. So what we know at the beginning? We know the initial activity of our aqueous phase, that is equal to 3,000 becquerel. Okay. How to calculate the activity of aqueous phase at the end of when the equilibrium will be reached? Again, as far as there is no carrier, that means that amount of the strontium bromide is very, very small. That means that at equilibrium, the activity should be equal almost to 0 becquerel. If we remember again the equation for degree of isotope exchange, I will write it now in correct form. It will be simplified as far as it is equal to 0. We can rewrite it and we can put the A0 in the first place. A0. So we know the activity of aqueous phase at a time after 9 hours. But we have to recalculate this A0, or let's call it A total, due to the decay of our bromine. So let's recalculate it. So I will call it A0 asterisk. So it will be our A0 multiplied by the exponent minus lambda t, or in this case, it's not very convenient, so we will take this equation. So it will be 3,000 becquerel multiplied by the exponent minus logarithm 2 divided by 36 hours, so it's half-life, and multiplied by the time that is passed. So it will be 2523, let's say, becquerel. And thus, we should take this number instead of 3000 to calculate the degree of isotope exchange. So it will be minus 500 divided by, so it will be equal to 0.8. If we didn't take into account this change in activity, we could get the wrong number, so it would be divided by 3000. It will be so very close. But still, if the time would be, for example, 18 hours or other more longer period of steering, then it would be it would take even more dramatic effect in calculations, because we should always take into account the half-life of our radionuclide. If the time of observation or performing the experiment or measuring is comparable to the half-life of the radionuclide. Okay, let's go to the next task. Here it seems maybe more complicated task, but it is not that difficult. So we have a vessel where the barium carbonate labeled with carbon-14 is located, and we fill this vial with stable carbon dioxide, close it hermetically, seal it, and then kept for several hours at elevated temperature. And after a certain time, the activity of our initial barium carbonate decreased by 1.25 times. And we have to determine the degree of isotope exchange. So, what we know? We know the mass of barium carbonate. Thus, we can find the amount of barium carbonate in the system. It will be mass divided by the molar mass. So it is 296 milligrams, so 10 to minus 3 grams. Divided by the molar mass, it is 137 plus 12 plus 48. So it will be 10 to minus 3 divided by so it will be 1.5 10 to minus 3 mole. What else we know? We know the volume of our vessel or reactor. We know temperature, we know pressure, and thus we can find the amount of carbonate gas, carbon dioxide gas, by this equation. So it is equation where if you know the pressure, the volume, it is a constant gas, a universal constant, and temperature, you can find the number or the amount of CO2. So it will be pressure, volume, divided by this. So pressure is 99 kilopascal, so 10 to 3. Volume is 50, but we have to convert it to liters. This constant is joule divided by mole per Kelvin. And here's temperature, and temperature should be expressed in Kelvin. So it is 24 Celsius degrees plus 273. Also, we have to convert liters to cubic meters because, for example, Pascal, it is Newton divided by squared meters, and thus we have to convert liters to cubic meters, so it again 10 to minus 3. So it will be 2 10 to minus 3 mole. Okay, now let's not forget this equation. The degree of isotopic exchange will be activity at our moment. So what will be the activity? We know the activity at the moment. It is simply A0 divided by 1.25. So we have to calculate a activity of barium carbonate at equilibrium. If we know the total activity, so it is our initial activity of barium carbonate, there is no other activities inside our system. And now we have to take this fraction of a number of carbon atoms divided by the total atoms in the system. So it is simply this expression. And we already know all the numbers, so it will be A0. Here it is 1.5 10 to minus 3. And here the sum will be 3.5 10 to minus 3 A0. Something like this. Now we can calculate the degree of isotope exchange. So AT, it is A0 divided by 1.25. So it is 450. And let's put all these numbers in our equation. So of course all this A0 will be annihilated, neglected. So it will be 1.5 and divided by 4.7 or just 7/20 or 0.35. So here again you can see that even if we don't know the exact activity of our carbonate, we can determine the degree of isotope exchange. Also, it is interesting that we can say that solid compounds, they're more or less inert in reactions with some gases. So barium carbonate is insoluble solid, so it doesn't react actively even with water, and with carbonate it should be no reaction. But you can see that the isotope exchange, it's a bit different situation. It's not just it's like a chemical reaction, but in this case it is a exchange of groups of CO2 groups in the solid and the gas. And with these techniques, when using the isotope exchange techniques, these radioactive traces, you can investigate the processes that are very slow, that can be not detected by the, let's say, convenient, common analytical techniques. So what is the rate of exchange of carbon dioxide? What is the reaction rate of carbon dioxide with barium carbonate? It is very difficult to investigate with the common analytical techniques, but with the use of radioactive tracer, you can see it. And if it would be information about the time that we passed, that was passed, then we can calculate the constant rate of this process. But we will do it in the next task. So, and we will go back to one of our first tasks that we already solved. We determined that in this case the degree of isotope exchange is 0.5, and how to calculate what the degree of isotope exchange will be after 8 hours, for example, or when the equilibrium will be reached. To do this, it is assumed that many of the reactions of isotope exchange, they depend only on one component, because radionuclide, it is usually the amount of radionuclide is very small, and thus we can neglect the presence of a big amount of stable atoms. Now, why it is so? When we write the equation for the rate of chemical reaction, we can write it as so it's concentration of component A in the let's call it alpha degree, and component B with the index beta. Usually this alpha and beta, the natural values, so natural, so it's maybe 0, 1, 2, etc. And if the amount of component A is much less, so the concentration is much less than concentration of component B, that means that all the reactions, they will not cause a significant changes in the concentration of component B. So this value will be more or less constant during time, and thus we can neglect it. And taking into account this, we can write it like in the degree alpha. And as far as it is only single atoms per one reaction is exchanged, it is so alpha and beta, they are called order of the reaction. And as far as it is only one molecule or one atom, let's say, we can write it as a reaction of the first order. So it is number 1. What is the rate of the chemical reaction? It is change of concentration of our component with time. And you can see that the solution of this differential equation, it is the exponent or natural logarithm. Finally, when we express how the concentration is changes with time, we will find the simple equation for the rate of isotope exchange. That is very similar to the part of the equation when we talked about the secular equilibrium and the accumulation of the daughter radionuclide. I will remind you that it was like this. The only difference that in this case lambda it's decay constant, and here k it is the isotope exchange constant. So if we know, yes, for example, if the degree of isotope exchange is 0.5, with the, and we know that time of this exchange, we can find that this constant k will be equal to logarithm 2 divided by this time when the isotope exchange is equal to 50%. So again, it is very close or the same equation as for decay constant for lambda, where it is logarithm 2 divided by the half-life. So all the mathematical consequences will be the same. Thus, as far as we know that after 2 hours the isotope exchange is equal to 50%, that means that we know this, let's say, not a half-life, but time of the half of isotope exchange. And thus, we can also rewrite this equation as this, minus the same as in the case of radioactive decay. And thus, we can find this isotope exchange degree after 8 hours as a degree of 2. So again, we already know that after 2 hours the degree of isotope exchange is 0.5. We know it already, and we are asked what will be after the 8 hours. So after 8 hours, it is 2 to minus 3, or minus 4, sorry. And it will be 1 minus 1 divided by 16, so it is 15/16, or so it is more than 90%. Let's find the exact number. Oh, 0.375. So it is 9 or we can write it as 93.75%. Again, the same situation as in the case of radioactive decay. We can reach the equilibrium, more or less, after, let's say, 10, not half-lives, but 10 periods of the half of the isotope exchange. So in this case, as far as this time is equal to 2 hours, we can say that after 20 hours we will reach the equilibrium for isotope exchange. So I hope that it could be not very clear in the beginning, but we will practice more with these tasks next time, and I hope it will be more clear. Okay, that is all for today. Thank you for your attention, and see you next week.